24 billion kilometers from Earth. Its transmitter runs on less power than the light bulb in a refrigerator. And somehow, we can still hear it. The signal hitting our antennas right now left Voyager 1 nearly 24 hours ago. It has been traveling at the speed of light for an entire day. And we only just received it. So how are we still in contact? To understand that, you have to go back to 1964. A student at JPL noticed something hidden in the math, a planetary alignment so rare it only occurs once every 176 years. Jupiter, Saturn, Uranus, and Neptune lining up so perfectly that a single spacecraft could slingshot between all four, using gravity as fuel. A journey that would normally take 30 years compressed into just 12. NASA planned for spacecraft. A grand tour of the outer solar system. Then the Apollo budgets were slashed for the shuttle program. They got to probes. That was the compromise. Each one carried a golden record, images, sounds, and greetings meant to represent all of humanity. Though the primary mission was simpler, get close to Jupiter and Saturn, and come back with data. Voyager to launch first in August 1977 on a slower trajectory designed to visit all four planets. Voyager 1 followed weeks later on a faster path. Together, they delivered the first close-up images of the outer planets. They caught active volcanoes erupting on Jupiter's moon Io, something nobody had predicted. They made the first and only visit to Uranus and Neptune. And then Voyager 1 captured it. The pale blue Earth, suspended in a sunbeam, as the probe turned its camera one last time before heading into the dark. Saturn swung Voyager 1 north, out of the solar system, 17 kilometers per second. No brakes, no return. It will fly that path forever. Voyager 2 headed south, opposite direction, same fate. Now here's the engineering problem that keeps physicists up at night. Each Voyager carries a 3.7-meter dish antenna behind it. A transmitter barely powerful enough to light a small fridge. Bulb. That's the signal it's sending across 24 billion kilometers of empty space, just screaming into the void, hoping someone is listening. On Earth, NASA built the answer. The Deep Space Network. 3 complexes, equally spaced around the planet. One in the California desert, one outside Madrid, Spain, one near Canberra, Australia, positioned 120 degrees apart so that as Earth rotates, at least one antenna always has line of sight to any spacecraft in the solar system. These antennas are extraordinary machines. The receivers are cooled too, just 4 degrees above absolute zero. At those sensitivities, even the warmth of the electronics themselves would drown out Voyager's whisper. By the time that signal arrives at Earth, it's carrying less than 1 attowatt of power, a billionth of a single watt, 20 billion times weaker than a digital watch battery. The 70-meter parabolic dishes gather every radio wave that touches their surface and focus it onto a single hypersensitive receiver. And even then, it's barely enough. There's another complication. Voyager is moving so fast that its signal arrives Doppler shifted, the same effect that stretches light from distant galaxies. The team has to compensate for that shift in real time just to decode what the probe is saying. The one-way travel time from Earth to Voyager 1 is 23.5 hours. Send a command on Monday morning. See the result Wednesday morning. That's the communication loop keeping humanity connected to the farthest object it has ever built. And those same 70-meter dishes that listen can also transmit at over 1,000 times the power of Voyager. Whisper. Inside those probes, the computing power is almost incomprehensible by modern standards. All 6 of Voyager's computers combined have 68 kilobytes of memory, less than an electronic car key. Your phone has 2 million times more processing power. And yet NASA's engineers have been sending software updates to these probes for nearly 50 years, patching glitches and compensating for broken hardware from billions of kilometers away. Each Voyager runs on 3 radioisotope thermoelectric generators, nuclear batteries powered by decaying plutonium. At launch, each probe had 470 watts. Today, barely 210 remain. Only 3 of the original 11 science instruments are still running. Every year, the team shuts down another one to conserve power, choosing which sensors to silence on a spacecraft that is never coming home. One of those instruments, the long magnetometer boom, confirmed the exact moment Voyager crossed into interstellar space, detecting a shift in the magnetic field that proved it had left the sun's influence entirely. Keeping this connection alive has not been clean or easy. It has been a series of near disasters, each one solved by a team of 10 people who refused to give up. 1978, a scheduling error on the ground. Voyager to win 7 days without hearing from Earth. The software panicked, assumed the primary receiver had failed, and switched to the backup. But the backup had a broken capacitor. It couldn't lock onto Earth's signal. When engineers forced a switch back to the primary, the fuses blew. The primary receiver was dead. 8 months after launch, Voyager 2 was stranded on a crippled backup radio. The team in Madrid had one idea. They began transmitting test signals, sweeping slowly through different frequencies, searching for the exact adjustment the broken receiver needed to hear them. Hours of attempts, and then Voyager to phone home. That workaround from 1978 is still how Voyager 2 communicates today, 5 decades later, on a jerry-rigged backup receiver. January 2020. A routine calibration roll, a command delay left to power-hungry systems running simultaneously. The spacecraft drew more power than it had, instantly. The safety software shut down all 5 remaining science instruments to prevent catastrophic failure. Messages took 17 hours each way. It took a week to fix it. 2022. Voyager 1 started transmitting gibberish. The system keeping it aimed at Earth was sending what looked like randomly generated data. The cause baffled everyone until they traced it. Voyager had started routing data through a dead computer, one that hadn't functioned in years. The dead machine was garbling everything before it reached the transmitter. To fix, tell it to use the right computer. Problem solved. From 24 billion kilometers away. 2023. Voyager 2 went deaf. For 2 weeks it wasn't receiving any commands, apparently misaligned. Its antenna no longer pointed at Earth. The situation was made worse by geography. Voyager 2 is heading south out of the solar system, which means it's only reachable from the Deep Space Network station in Australia. 2 weeks of silence. Then, a faint signal, a heartbeat from the depths of space. The next day, they did something they called an interstellar scream. They pushed transmission power to 250% and sent one command across the solar system. Aim the antenna back at Earth. It worked. Every time something breaks, this team of 10 somehow finds a way. After 48 years, the result has always been the same. Both probes are still talking. The day is coming when they won't be. The power is running out. The last instruments will go dark. The signal will fade. We would like to get them to the 50-year anniversary. Maybe a little longer. 2028, maybe 2030, but it's not going to go for much longer than about 5 years. And when the signal finally dies, the probes don't stop. They keep flying. 2 machines built in the 1970s, designed for 5 years, carrying our sounds, our images, our greetings, drifting through interstellar space at 17 kilometers per second. Long after the last instrument shuts down, long after the last signal fades, the Voyagers will still be out there, carrying the story of everyone who ever lived on this planet into the dark forever.